Lift a glass of water and you feel its weight settle into your wrist. Almost none of that weight comes from the matter you would point to if someone asked you where it lives. The quarks inside, the small hard particles most of us picture as the real stuff, account for only about 1% of the mass. The rest is energy. It is the churning of a field inside every proton, held there by a force that grows stronger the harder you pull on it. So this is a look inside the proton, and the picture there is far stranger than 3 marbles in a bag. It behaves more like a storm that never settles, and you are made of it. If you enjoy quiet, careful ideas like this one, take a moment to subscribe. We will build the whole picture slowly, one simple step at a time, beginning with a plain question. What is a proton made of, and how did anyone ever find out? Hold a glass of water in your hand and let your arm go loose. You feel something. Not the glass exactly, and not the water exactly, but a steady downward insistence in your wrist, a pull you have known since you were small enough to drop things. That pull has a source. Somewhere inside the water there is mass, and gravity is finding it. Ask where the mass sits and the answer seems easy. Water is made of molecules. Each molecule is 2 hydrogen atoms and 1 oxygen atom. Each atom has electrons drifting around a nucleus, and the nucleus holds protons and neutrons. The electrons are almost weightless by comparison, about 1 part in 2,000 of a proton. So nearly all of the mass in your hand lives in the nuclei, in those protons and neutrons, packed so tightly that if you removed the empty space from every atom in your body, you would fit inside a grain of sand. That much has been settled for a century. The trouble starts one step further down. A proton is not a solid pellet. It has contents. Since the middle of the 1960s, we have known that inside every proton there are quarks, and the standard picture puts 3 of them there, 2 up quarks and 1 down quark, held together by a force. If you have seen a diagram of a proton, you have probably seen 3 coloured spheres nestled in a circle, sitting still, looking like marbles in a bag. Take those 3 quarks and add up their masses, you get about 1% of the proton, not 90%, not half, about 1. The particles we call the proton's building blocks supply almost none of the proton's weight. Whatever you feel in your wrist when you hold that glass, it is not coming from the stuff inside. It is coming from something else in there, something that has no mass of its own, moving so violently and so fast that its energy shows up on a scale as weight. The proton is not a bag of marbles, it is closer to a storm. The 3 quarks are real, and they matter enormously, but they are the least of what is happening inside. This is not a fringe claim or a new one. It comes out of quantum chromodynamics, the theory of the strong force, and it has been checked against experiments at Stanford and Hamburg and Geneva, and calculated from first principles on supercomputers by physicists in Japan and Germany and the United States. The number keeps coming out the same. The mass of the proton is mostly not made of massive things, and a proton is not an exotic object. There are roughly 10 to the 28th of them in your body. Nearly every kilogram you've ever lifted, every kilogram you carry around, is that same storm repeated past counting. So the everyday picture is not wrong so much as it is thin. You have a real intuition about mass, built from a lifetime of carrying groceries and lifting children, and feeling the world resist you. That intuition says that heavy things are heavy, because they are made of heavy things, all the way down. It is a good intuition. It works at every scale you can see. It fails at the last step. What replaces it is stranger and more beautiful, and it took about 70 years and several generations of physicists to assemble. It involves a force that grows stronger as you pull things apart. It involves particles that carry the very charge they respond to, so that the force feeds on itself. It involves a vacuum inside the proton that is not empty and never rests. We're going to build that picture from the ground, one step at a time, in the order the world revealed it. And the ground is a piece of gold foil in a laboratory in Manchester, England, being shot at with a radioactive source by a young man sitting in the dark counting flashes of light. The room had to be completely dark, and the eyes had to adjust for half an hour before the work could start. This was Manchester in the years around 1909. Ernest Rutherford, a large, loud New Zealander with a farmer's build and a booming voice, had set his assistant Hans Geiger and an undergraduate named Ernest Marsden a fairly dull job. They had a source of alpha particles, which are helium nuclei thrown out by radioactive decay, moving fast. They had a very thin sheet of gold, hammered down to a few thousand atoms thick, and they had a small screen coated in zinc sulfide, which gives off a tiny spark of light where an alpha particle strikes it. The job was to send the alpha particles through the foil, watch where they came out, and count the sparks by eye, one at a time in the dark for hours. The expectation was simple. The atomic model of the day came from Joseph John Thomson, who had discovered the electron a decade before. Thomson pictured the atom as a diffuse ball of positive charge with electrons embedded in it, a soft and rather democratic arrangement, sometimes called the plum pudding. Nothing in that atom is hard. An alpha particle ploughing through a foil of such atoms should be nudged slightly off course by the electric fields it passes, deflected by a fraction of a degree, and continue on. Most of them did exactly that. Then Marsden, checking the wide angles because Rutherford had suggested it as a matter of thoroughness, saw sparks where no spark should be. Alpha particles were coming back. Not many, about 1 in 8,000. But some of them were bouncing off the foil and returning toward the source. Rutherford later said the result was as astonishing as firing a large naval shell at a sheet of tissue paper and having it come back and hit you. He was not exaggerating for effect. An alpha particle leaves a radioactive atom carrying enormous energy for its size, and there is nothing in a pudding of smeared charge that could turn it around. To reverse it, you need to concentrate the atom's positive charge into a region small enough and dense enough that the electrical repulsion becomes overwhelming at close range. It took Rutherford almost 2 years to work out what the numbers demanded, and when he did, the answer was severe. Nearly all the mass of the atom and all of its positive charge sits in a core so small that if you scaled the atom up to the size of a cathedral, the core would be a fly hovering in the nave. Everything else is electrons and distance. Think about what that means for the gold foil. The alpha particles were not being slowed by a substance. They were flying through mostly nothing, and once in a long while one of them happened to aim straight at nucleus, and the electric repulsion between two positive charges spat it back the way it came. Rutherford published the nuclear atom in 1911. It solved one problem and created a worse one, which he seems to have felt immediately. If the core is positive and tiny, and if positive charges push each other apart, then any nucleus with more than 1 unit of positive charge should tear itself to pieces instantly. Gold has 79 of them. The nucleus of a gold atom should not survive a single moment. It survives for longer than the universe has existed. Something inside that core is holding it together against a repulsion strong enough to reverse a naval shell. And to look for it, physicists first had to know exactly what the core was made of. The war took Rutherford students. By 1917, Geiger was in the German army, Marsden was in France, and Rutherford was in Manchester on his own, doing work for the Admiralty on detecting submarines by sound. In whatever hours he could find, he went back to the bench. He had a simple apparatus, a brass box, a radioactive source of alpha particles at one end, a scintillating screen at the other, and gas in between. The alphas were fired into the gas. Rutherford watched for sparks at distances far beyond where an alpha particle could possibly reach, because alphas are heavy and lose their energy quickly. Anything arriving at the far screen had to be something lighter, moving faster, knocked forward by the collision. With hydrogen in the box, he saw those distant sparks, and that made sense. An alpha striking a hydrogen nucleus punches it forward like a cue ball. With dry air, he saw them too, which did not make sense. Then he narrowed it down. The sparks came when there was nitrogen in the box. The alpha particles were striking nitrogen nuclei and knocking hydrogen nuclei out of them. This was the first time anyone had changed one element into another on purpose. Rutherford had cracked nitrogen and found hydrogen inside, which meant the hydrogen nucleus was not merely one nucleus among many, but a piece of the others, a component. He published in 1919, the year he moved to Cambridge to run the Cavendish Laboratory. Around 1920, in a lecture to the Royal Society, he proposed a name for the particle, taken from the Greek word for first, the proton. There is a story about him from this period that physicists still tell. Summoned to a committee meeting on anti-submarine research, he arrived late and offered as his excuse that he had been busy splitting the atom. If that were true, he said, it was more important than the war. It sounds like bluster. It was roughly correct. So the picture sharpened. Every nucleus contains protons, each carrying 1 unit of positive charge, each about 1,836 times the mass of an electron. The number of protons decides the element. 1 proton is hydrogen, 2 is helium, 6 is carbon, 79 is gold, and nothing you can do chemically will ever change that, because chemistry only touches the electrons far outside. But the masses did not add up. Helium has 2 protons and weighs about 4 times as much as hydrogen. Something else was in there, something heavy and electrically neutral, and it stayed hidden for another 12 years until James Chadwick, who had been a prisoner of war in Germany and had learned his physics partly in an internment camp, identified the neutron at the Cavendish in 1932. Now the nucleus was complete, at least on paper. Protons and neutrons packed into a sphere a few femtometers across. A femtometer is 1 quadrillionth of a meter. If a proton were the size of a marble, the atom around it would be a few kilometers wide. And the old problem, the one Rutherford had created and left standing, became urgent. All those protons, positive, jammed together at a distance where the electric repulsion between any two of them is not a whisper but a scream. To understand how much they hate each other, you have to look at the electric force at that scale and see how absurd the numbers get. Charge is the property that makes things push and pull without touching. 2 negatives push apart, 2 positives push apart, opposites attract. Charles-Augustin de Coulomb, a French military engineer, measured the law in the 1780s with a torsion balance, a thin fibre that twists when a charged ball is pushed. He found that the force falls off with the square of the distance. Move 2 charges twice as far apart and the force drops to a quarter. Read that in reverse and it becomes alarming. Move 2 charges 10 times closer and the force multiplies by 100. Move them 100 times closer and it multiplies by 10,000. Inside a nucleus, protons sit about 1 femtometer apart. Put that number into Coulomb's law, and the electrical repulsion between 2 protons comes out at roughly 200 newtons. That is a force you could measure with a bathroom scale. It is about the weight of a 20-kilogram child. 2 specks, each of them 100,000 times smaller than an atom, are shoving each other with the force you would feel holding a toddler at arm's length, and they do not fly apart. A uranium nucleus contains 92 protons, all pushing on all the others, and it can sit in a rock in the ground for billions of years. Whatever is holding it must be stronger than that repulsion, and it must be stronger by a wide margin, because uranium is the fragile end of the scale. Iron nuclei are so tightly bound that stars stop burning when they reach them. Now notice what this force cannot be. It cannot be gravity, which between 2 protons is weaker than their electrical repulsion by a factor of about 10 to the 36th. Gravity is so feeble at this scale that it plays no part at all. It cannot be magnetism, which is the same electromagnetic force wearing a different hat. And it cannot be anything that reaches very far, because if it did, we would notice. Nuclei in a bar of iron would attract each other across the metal. Chemistry would be nothing like chemistry. 2 lumps of matter brought together would slam into one another and fuse. So the thing holding the nucleus is strong, and it is short. It has to be overwhelming at 1 femtometer and effectively absent at 10. That combination has no analogue in ordinary life. Every force you have ever felt, from magnets to gravity to the pull of a rope, fades gradually. This one falls off a cliff. You can almost feel the shape of it in the way nuclei behave. Small nuclei are stable with equal numbers of protons and neutrons. Large ones need more and more neutrons to survive, because neutrons feel the strong attraction, but carry no charge and add no repulsion, so they act as a kind of glue. Past a certain size, no amount of glue is enough. The nucleus is too wide, the electrical repulsion reaches across it, and the strong force does not. That is why uranium fissions and why there is a heaviest element at all. By the early 1930s, physicists had a clear list of properties for a force nobody understood, held by a nucleus nobody could open. Neutrons and protons stick to each other and to themselves, hard at a femtometer and not at all beyond it. And then a young Japanese physicist, working almost alone, asked what kind of particle would have to be passing between them to produce a force shaped exactly like that. Hideki Yukawa was 27 years old, shy, prone to long silences and teaching in Osaka. He had failed to make much of an impression on his more assertive contemporaries. In 1934, he was thinking about a question that sounds abstract and turns out to be the whole game. What is a force, physically? Quantum field theory had a strange answer already for electromagnetism. Two electrons repel because they exchange photons between them, particles of light passing back and forth, carrying momentum, pushing the electrons apart in the way that two people on ice throwing a ball at each other drift apart. The photon has no mass, and that is why the electric force reaches forever. Nothing limits how far a massless particle can travel. Yukawa turned the reasoning around. If a massless carrier gives an infinite range, then a massive carrier gives a finite one. Quantum mechanics allows a particle to be borrowed from nothing for a brief instant, so long as it is repaid quickly, and the heavier the particle, the shorter the loan, and the less distance it can cover before it must vanish. Range and mass are inversely tied. He knew the range he needed, about 1 femtometer. He put it in, turned the crank, and out came a mass, roughly 200 times the mass of the electron, somewhere between an electron and a proton, sitting in a gap in the particle list that nobody had noticed was empty. He called it a mesotron, later shortened to meson from the Greek for middle. He published in 1935 in the Proceedings of the Physico-Mathematical Society of Japan, a journal almost nobody outside Japan read, and for 2 years the paper sat there unnoticed. Then, in 1936, Carl Anderson and Seth Neddermeyer, studying cosmic rays at Caltech with a cloud chamber on Pikes Peak, found a particle with about the right mass. For a decade it was assumed to be Yukawa's. It was not. This particle barely interacted with nuclei at all, which made it useless as the glue. Isidore Rabi is said to have greeted its confirmation by asking who ordered that. It was the muon, a heavy cousin of the electron, and it had nothing to do with the strong force. The real one turned up in 1947. Cecil Powell in Bristol, working with Giuseppe Occhialini and Cesar Lattes, coated photographic plates with thick emulsion and carried them to mountaintops, to the Pic du Midi in the Pyrenees, and then to Chacaltaya in the Bolivian Andes, 5,000 meters up, where cosmic rays arrive before the atmosphere has scrubbed them. Developed and read under a microscope by teams of women employed as scanners, the plates showed a track that stopped and gave birth to a second track, a heavier particle decaying into the muon. That was the pion. Its mass is about 273 times the electrons. Yukawa had been close enough to be right. He received the Nobel Prize in 1949, the first Japanese citizen ever to win one, 4 years after the end of a war that had left his country's physics community in ruins. For a while it seemed done. The strong force was pion exchange. Protons and neutrons toss pions back and forth, and the nucleus holds. The trouble was that the mountaintop plates and the new machines being built in California did not stop at the pion. They kept producing particles, dozens of them, and none of them fit anywhere. The cloud chamber was a beautiful instrument, supersaturated vapor in a sealed box, and a charged particle passing through leaves a trail of droplets behind it, a white thread hanging in the air, curving if you apply a magnetic field. The curvature tells you the charge and the momentum. You photograph the thread, and you have measured a particle you cannot see. In 1947, at Manchester again, George Rochester and Clifford Butler photographed something odd. A thread appeared out of nowhere and split into a narrow V, 2 tracks springing from an empty point. Something neutral, leaving no trail, had travelled through the chamber and decayed into 2 charged particles. They found a second event, then others, and the masses came out near 1,000 times the electrons. Nobody had asked for these. They were produced readily by the strong force, which meant they were strongly interacting, but they lived far longer than they should have before decaying, about a 10/1000th of a second, which is an eternity by the standards of the strong force. They were called strange particles, and the name stuck, and eventually strangeness became a genuine quantum number that had to be conserved. Then, the machines arrived. The Bevatron at Berkeley, finished in 1954, could push protons to 6 billion electron volts, and it had been designed with exactly enough energy to make an antiproton. Owen Chamberlain and Emilio Segre found it in 1955. The Cosmotron at Brookhaven, the synchrotrons at CERN, each new machine opened a new energy range, and each new energy range was full. Kaons, lambdas, sigmas, z's, deltas, rho mesons, omega mesons, particles that lived for 100 millionth of a second, and particles that lived for a billionth of a second, so briefly that they never travel far enough to leave a track and are seen only as a bump in a graph. By the end of the 1950s there were dozens. By the mid-1960s there were more than 100. They could not all be elementary. The whole point of an elementary particle is that there are few of them, and that everything else is built from them. Enrico Fermi, asked to name them all, said that if he could remember the names of all these particles he would have become a botanist. It was a joke with an edge in it. Botany is what you do when you have no theory, only specimens. There was structure in the mess though, if you squinted. The particles came in families. Within a family the masses were close, and the members differed by their electric charge. The proton and the neutron differ in mass by about 1 part in 700. The 3 pions, positive, negative and neutral, cluster tightly. The sigma baryons come in 3, the xi's in 2. Werner Heisenberg had noticed the proton and neutron pairing as early as 1932 and called it isospin, treating them as 2 faces of one particle, the way an electron has 2 spin states. Nobody knew why nature was arranging things this way. Whenever a list of objects falls into neat families with repeating patterns, someone eventually notices that the pattern comes from a smaller set of pieces underneath. It happened with the elements, where Dmitri Mendeleev's periodic table turned out to be counting electrons and protons. Now it was going to happen again, and the pieces underneath would be so peculiar that the 2 men who proposed them would spend years insisting they might not be real. Murray Gell-Mann was a difficult, brilliant man at Caltech who collected languages and birds and corrected people's pronunciation of their own surnames. In 1961 he found a way to sort the particle zoo, arranging the mesons and baryons into geometric patterns on a page, hexagons and triangles, with the particles at the vertices in the centre. The mathematics behind it was a group called Special Unitary Group of Degree 3, but the arrangement itself you could see with your eyes. Yuval Ne'eman, an Israeli military officer turned physicist, found the same scheme independently in London. Gell-Mann called it the Eightfold Way, borrowing lightly from Buddhism, and the joke was that the fundamental patterns held 8 particles. Then one of the patterns came up short. A triangular array of 10 baryons had 9 members and a hole at the bottom vertex. Gell-Mann read off from the geometry what the missing particle's charge, strangeness, and mass had to be. He predicted the omega minus. In 1964 at Brookhaven, a team scanning bubble chamber photographs found it, with the mass he had named, and the pattern closed. A pattern that predicts is a pattern with something behind it. The question was what? In 1964, Gell-Mann and independently George Zweig at CERN gave the same answer. All these particles are combinations of a few smaller ones, 3 of them at that time. Take the up, the down and the strange. give the up a charge of positive 2/3, and the down and the strange a charge of negative 1/3. Build every baryon out of 3 of them, and every meson out of 1 quark and 1 antiquark, and every family in the eightfold way falls out of the arithmetic. A proton is 2 ups and a down. 2/3 plus 2/3 minus 1/3 is 1. A neutron is 1 up and 2 downs, and its charge is 0. The pion is a quark and an antiquark. The omega minus is 3 strange quarks, which is why it was the loneliest corner of the pattern. Gell-Mann took the name from a line in James Joyce's Finnegan's Wake that mentions 3 quarks. Zweig called them aces, and his name did not survive. Zweig had the harder time of it. His paper was never accepted by a journal, and a senior theorist at CERN reportedly dismissed him as a charlatan. He eventually left particle physics and went to study the human ear. The fractional charges were the scandal. Every charge ever measured, from Robert Millikan's oil drops onward, had come in whole units of the electron's charge. Now the theory required thirds, and no experiment had ever seen a free quark, then or since. So Gell-Mann hedged. He wrote about quarks as mathematical devices, useful for bookkeeping, possibly not physical objects at all. It was a reasonable position. The scheme worked beautifully as an accounting system, and there was no evidence that the accounts corresponded to anything you could hit, which is precisely what you go and check. If a proton has hard little pieces inside it, then fire something small and fast into a proton and watch how it comes out. That is Rutherford's experiment again, one level down, with the proton playing the part of the atom. They built the machine for it in a valley in California, 2 miles long, pointed at a bottle of liquid hydrogen. The Stanford Linear Accelerator runs under a highway in Menlo Park, straight as a rifle barrel for 2 miles, the longest building in the world when it was finished in 1966. Along its length, microwave power pushes electrons forward in step, accelerating them to 20 billion electron volts. At the end, the beam struck a target of liquid hydrogen, which is to say a target of protons, and the scattered electrons flew into enormous steel spectrometers mounted on rails, weighing hundreds of tons that could be swung to different angles and rolled into place. The team included Jerome Friedman and Henry Kendall from the Massachusetts Institute of Technology and Richard Taylor from Stanford. The experiment was not designed to find quarks. Nobody expected to. Deep inelastic scattering, where the electron hits the proton hard enough to shatter it, was regarded as a messy background, and the interesting measurement was thought to be elastic scattering, where the proton survives. The received wisdom was that the proton was a soft, smeared object. Earlier work by Robert Hofstadter at Stanford, with lower energies, had already shown that the proton was not a point. It had a size, about 8/10 of a femtometer, and its charge was spread out through that volume like pudding. Fire an electron at a diffuse cloud of charge, and it should mostly pass through, deflecting a little. Hard scattering at large angles should be extremely rare, falling away sharply as you pushed a higher momentum transfer. In 1967 and 1968, the counters at large angles kept clicking. Electrons were bouncing back at rates far above what a soft proton allowed. The fall-off that everyone expected did not happen. Kendall later described the feeling of it by pointing back 60 years to Manchester. Rutherford's alphas came back because the atom had a hard core. These electrons were coming back because the proton had hard cores, plural, small and point-like, and an electron once in a while happened to strike one of them squarely and ricochet. The measurement said more than that. The rate at which electrons scattered depended on how the proton's insides shared momentum, and the pattern that emerged said the scattering was happening off objects with spin 1/2, like the electron itself, and effectively point-like down to the resolution of the beam. Not lumps, not a fluid. Constituents. There is a caution worth keeping. Nothing in the data had a label reading quark. It showed that something inside the proton was small and hard and carried a fraction of the momentum. Connecting that to Gell-Mann's fractional charges took several more years of measurement, including neutrino scattering at CERN and precise comparisons between protons and neutrons, before the constituents' charges were pinned to 2/3 and -1/3. But the door was open, and everyone knew it. Friedman, Kendall and Taylor shared the Nobel Prize in 1990. What made the results hard to interpret was a contradiction sitting inside them. The electrons behaved as though they were striking free particles, unbound, rattling around loose inside the proton, yet no experiment anywhere could pull one out. Whatever holds quarks inside a proton is so strong that nothing has ever escaped it, and the same quarks act when you look at them closely, as if nothing is holding them at all. Understanding that took a change in how physicists pictured what was going on inside during the instant of collision, and it began with Richard Feynman, who was not thinking about quarks when he thought of it. Richard Feynman came to Stanford in the late summer of 1968. James Burkert, the theorist who knew the scattering data best, happened to be away. So Feynman spent his time talking with whoever was around, looking at the plots, and, by his own account, working out the problem partly in a bar in Palo Alto, which was where he liked to do his thinking. He had not come to think about the proton's interior. He had been chewing on a different question, about what happens when two protons smash into each other at very high energy, and he had convinced himself of a way to picture any fast-moving proton. He supposed it was made of some number of small pieces, and he refused to say what they were. He called them partons, from the word part, which is about as non-committal as a name can be. Whether they were Gell-Mann's quarks he left open, and there was some professional coolness between the two men that made the refusal easier. The heart of the picture is what relativity does to a proton moving near the speed of light. Two things happen. It flattens along its direction of travel, squashed into a thin pancake, and its internal clock slows down. Whatever the pieces inside are doing, whatever furious exchange of forces going on among them, all of it runs in slow motion as seen from the laboratory. Now the electron arrives. It crosses that flattened pancake in an unimaginably brief instant, far shorter than the time the pieces inside would need to notice each other, to pull on each other, to react. During the collision, each parton is effectively alone. It does not know it is bound. It gets struck as a free particle would be struck, and it is only afterward, in the long, slow aftermath, that the strong force reasserts itself and drags everything back together into a spray of ordinary particles. Think of photographing a hummingbird's wings. At an ordinary shutter speed you get a blur, a smear where a wing should be, and you might reasonably conclude the bird has no wings at all, only a fog around its shoulders. Open the shutter for a millionth of a second and the wing is there, sharp, an object with edges. Nothing about the bird changed. The blur was in the looking. The electron beam at Stanford was a fast shutter. It caught the parton still. That is why the scattering could show hard, point-like targets, even though nobody could pull one out. The electron does not measure whether a quark is bound. It measures what the quark is doing during a time so short that binding has no chance to matter. Feynman turned this into a way of calculating. Assign each parton a fraction of the proton's total momentum. Call that fraction x. The struck parton carries some x, and the electron, by how far it is deflected and how much energy it loses, tells you what that x was. Collect millions of collisions and you build up a distribution, a curve showing how the proton's momentum is shared out among its contents. Some partons carry a lot, some carry very little, and the shape of that curve is the proton's fingerprint. Physicists still measure it today and still call the variable x. The comparison to Rutherford holds only so far, and it is worth marking where it breaks. Rutherford's alpha particle bounced off a nucleus, and the nucleus stayed a nucleus. When an electron strikes a parton hard, the proton does not survive. It is torn apart, and what emerges from the wreckage is a shower of pions and other hadrons, dozens of them, none of which is the thing that was hit. The struck parton never appears. You infer it from the electron alone, from the one particle that left cleanly. Burkert, before any of this, had already noticed something remarkable hiding in what the data ought to look like. and what he noticed was that a certain measurement should stop depending on the energy of the beam altogether. Here is the strange thing Burkert predicted, and it is easier to feel if you first consider what ordinary objects do. Look at something with a size: a raindrop, a marble, a nucleus. How it scatters a beam depends on how the size of the object compares to the wavelength of what you're shooting at it. Use a long wavelength and you see a blur, a single soft lump. Shorten the wavelength and structure appears, and the pattern of scattering changes and changes again as you keep shortening. The object has a scale built into it, and every measurement you make knows about that scale. Now suppose the thing you are hitting has no scale. Suppose it is a point. Then there is nothing for the wavelength to be compared against, and the scattering stops caring how hard you hit it. It becomes the same at every energy. Burkert worked this out in 1968, writing down what the proton's response should look like if its contents were point-like. The measured quantity depends, in general, on two independent numbers: how much momentum the electron delivered and how much energy it lost. Burkert predicted that the answer would not depend on those two separately at all. It would depend only on their ratio, that single fraction x, the share of the proton's momentum carried by whatever got struck. Double the beam energy and hit twice as hard, and as long as x stayed the same, you would get the same answer. This is called Burkert scaling, and when Friedman, Kendall and Taylor plotted their data, it was sitting there. The curves from different beam energies fell on top of each other. Emanuel Pascos and Burkert then showed how the parton picture produced scaling naturally, and the two ideas locked together. So the proton's contents were points. Not small spheres, not soft clouds, but objects with no measurable size at all, which is still true today. The quark, so far as anyone has ever managed to measure, has no radius. The best limits say it is smaller than a 10,000th of the proton. Then came the bookkeeping, and the bookkeeping delivered a shock. Every parton carries some fraction of the proton's momentum. Add up all the fractions and you must get 1. That is not a physical law so much as arithmetic. The electron scattering measures the fractions of everything that carries electric charge, because electrons only feel charge. The experimenters added up what the charged partons carried. It came to about half. Half the proton's momentum was being carried by something the electron beam could not see. Something inside the proton, moving with it, holding a great share of its motion, and completely blind to electricity. Neutral. The neutrino scattering experiments at CERN, done in the Gargamel bubble chamber in the early 1970s, confirmed the missing half from an entirely different direction, since neutrinos probe the weak force rather than the electric one. There is a version of this story where the missing half is a mundane accounting error, some subtlety in the analysis. It was not. The other half of the proton is real, and it is not quarks. It is the force itself, made of particles carrying momentum filling the interior. Nobody had a name for it yet in the scattering data. The theory that would name it was being built at the same time, out of a problem that had nothing to do with momentum and everything to do with 3 identical quarks sitting in one place, doing something the laws of quantum mechanics say they cannot do. The omega minus, the particle Gell-Mann had predicted from a hole in a triangle, was made of 3 strange quarks. In its ground state, all 3 sit in the lowest energy configuration, and to give the particle the spin it actually has, all 3 spins must point the same way. 3 identical quarks, same place, same spin, same everything. Quantum mechanics forbids this. Wolfgang Pauli established the exclusion principle in 1925, and it says that no 2 identical particles of half-integer spin can occupy the same quantum state. This is not a small rule. It is why electrons stack up in shells instead of all falling to the bottom of the atom, and therefore why chemistry exists, and why you do not sink through your chair. The delta ++ is the same problem in a more common particle. 3 up quarks, spins aligned, a state that should not exist. It exists. It is produced by the ton in any accelerator that fires pions at protons. Something was badly wrong. Either the quark model was mistaken, or the exclusion principle failed inside the proton, or the three quarks were not actually identical and differed by some property nobody had discovered. Oscar Greenberg, at the University of Maryland, proposed the third answer in 1964, though he cast it in an unfamiliar mathematical language called parastatistics, which obscured the point. The next year, Mu-Young Han and Yoichiro Nambu, working in Chicago, put the idea in a form people could use. Nambu was an émigré from Japan, so quiet in seminars that colleagues sometimes could not tell whether he had understood or lost interest, and he had a habit of publishing ideas a decade before anyone else was ready for them. Give the quark a second kind of charge. Not electric charge, which the quark already has, a new one, unrelated, which comes in 3 varieties rather than 2. Then the 3 up quarks in the delta are not identical after all. Each carries a different value of the new charge, and Pauli is satisfied. Gell-Mann later named the varieties red, green and blue, and named the property colour. The words carry no meaning beyond bookkeeping. Quarks are far smaller than any wavelength of light, and colour in this sense has nothing to do with vision. The name was chosen because 3 of something combining to make a neutral something is exactly what red, green and blue light do when they overlap. Every particle we can observe, every proton and pion and omega minus, is colour neutral. Baryons take 1 quark of each colour. Mesons take a colour and its anti-colour. An invented property that fixes one problem is a suspicious thing. What made colour believable was that it fixed others it had not been designed for. When electrons and positrons annihilate at high energy, they sometimes make a quark and an antiquark. The rate at which this happens, compared to the rate for making a muon pair, is a pure number you can calculate from the quark charges. Without colour, the prediction is off. Multiply by 3, once for each colour a quark can wear, and the number matches experiment. The neutral pions decay into 2 photons is likewise too fast by a factor of 3 squared unless colour is there. So the quark carries a colour charge, 3-valued, hidden and conserved. Charges are the sources of forces. Electric charge is the source of electromagnetism, and it has one kind. This new charge should have a force of its own. That force needs a carrier, the way electricity has the photon, and the carrier turns out to be a particle unlike anything in the older physics, because it does not merely transmit the colour force, it carries colour itself. The photon is electrically neutral. This sounds like a technicality, and it is the reason electricity behaves politely. Photons pass through each other. 2 beams of light cross in a dark room and nothing happens. No scattering, no glow at the intersection. Light does not pull on light. The carrier of the electric force is blind to the force it carries. The carrier of the colour force is not. It is called the gluon, and its job is to move colour charge between quarks. A red quark emits a gluon and turns blue. The gluon that left is carrying the difference, red away and blue back, which means the gluon itself has colour, 2 units of it, a colour and an anti-colour. Because it is coloured, it feels the colour force. Gluons pull on gluons. A gluon can emit another gluon. Nothing in electricity does this, and it changes everything. The mathematics for such a force had been written down in 1954 by Chen-Ning Yang and Robert Mills at Brookhaven, for entirely different reasons, and it was almost strangled at birth. When Yang presented the work in a seminar at Princeton, Wolfgang Pauli interrupted from the audience to ask what the mass of the new carrier particle was. Yang said he did not know. Pauli pressed him again. Yang eventually sat down and would not continue. The theory required massless carriers, and massless carriers meant a long-range force, and no such force was known. It looked like a beautiful piece of mathematics describing nothing. It sat for 19 years. In 1973, Harold Fritsch, Heinrich Leutwiler, and Murray Gell-Mann put colour charge into the Yang and Mills framework and gave the result its name. Quantum chromodynamics, the quantum theory of colour, which everyone shortens to QCD. 3 colours of quark and 8 gluons to move colour among them. 8, not 9, and the missing one is worth a moment. 9 combinations of colour and anti-colour exist. One of those combinations is symmetric across all 3 colours, and it turns out to be colourless, a gluon that would carry no charge and would behave like a photon. If it existed, the strong force would reach across the room. It is not in the theory, and it is not in nature, and the fact that 8 is the right number is one of the quiet confirmations that the structure is correct. The gluons are massless, which by Yukawa's reasoning should give an infinite range. Yet the strong force between nuclei dies out past a couple of femtometers. Yukawa was not wrong about pions, which are massive and do set the range of the residual force that binds protons to neutrons. But the force underneath, between quarks, is carried by massless particles and still does not reach. The self-interaction is why. Because gluons attract gluons, the field between 2 quarks does not spread out into space the way an electric field does. It gathers itself. It pulls itself into a narrow tube. Meanwhile, the gluons inside a proton were still, in 1973, entirely theoretical. Something neutral was carrying half the momentum, which was suggestive, and the theory said gluons were there, which was suggestive. Nobody had seen one do anything. The way to see one is to knock a quark hard enough that it radiates a gluon before anything else can happen, and then look for the gluon's debris. That takes a very particular machine, and the Germans built it. When an electron meets a positron, they annihilate. Their entire mass and energy pour into a single photon, which promptly becomes something else, and one of the things it becomes is a quark and an antiquark, flying apart back to back. Neither one gets out. As they separate, the colour field between them stretches, and it breaks, and the breaking makes new quarks, and those pair up, and what emerges into the detector is 2 narrow sprays of ordinary particles, pions and kaons, travelling in the directions the original quark and antiquark went. Physicists call each spray a jet. The jet remembers the quark's direction the way a shotgun pattern remembers the barrel. 2 jets, back to back. This had been seen at Stanford in the 1970s, and it confirmed the quark picture nicely. But if gluons are real, then sometimes, before the quark has travelled anywhere, it should shake one loose. A quark accelerating away from its partner radiates gluons the way an accelerating electron radiates light. Most of those gluons are soft and merge into the existing jets. Once in a while, one of them comes off hard and at a wide angle, carrying a serious fraction of the energy. That gluon cannot escape either. It too dresses itself in ordinary particles. 3 jets splayed out in a plane like a peace sign. The machine was Petra at the German electron synchrotron in Hamburg, a ring nearly 2.5 kilometers around that began running in 1978, reaching energies where the effect should be visible. 4 experiments watched: Tasso, Mark J, Pluto, and Jade, competing and checking each other in a way that makes the result much harder to doubt. Xiaolan Wu, on Tasso, wrote the analysis that could tell a genuine 3-jet event from a 2-jet event that happened to look sloppy. She'd grown up in poverty in occupied and then post-war Hong Kong, sometimes sleeping in the back of a rice shop, and had come to the United States on a scholarship to Vassar after writing to 50 colleges asking for aid. She would later be part of the discovery of the Higgs boson as well. In 1979, the events appeared. 3 clean sprays, at the rate the theory predicted, and the angular distribution matched a spin 1 particle radiating from a quark. All 4 experiments saw them. Presented at a conference in Geneva that summer, the 3-jet event settled the question. The gluon is a particle you can point at in a photograph, which is a peculiar thing to say about something that has never been isolated and never will be. Notice how well the pieces now fit. Half the proton's momentum was missing and carried by something electrically neutral. Gluons are electrically neutral, and they're inside the proton in enormous numbers, and they carry momentum. The missing half found its owner. Still, the central paradox of the Stanford experiment was untouched. Inside the proton, the quarks behave as free particles drifting, barely aware of one another. Outside the proton, they cannot exist at all. A force that lets its captives roam and never lets them leave is not like any force in ordinary experience. And for a few years, nobody could show that quantum chromodynamics actually produce such behaviour. Then 3 young theorists, working on what their advisors thought was a doomed calculation, found that this theory does something no other theory does. Its force gets weaker as you get closer. Every force we know grows stronger as you close in. Move 2 magnets together, and the pull increases. Fall toward a planet and gravity rises. Push 2 electrons together, and the repulsion climbs by the inverse square. Quantum field theory adds a wrinkle to that last one. An electron in a vacuum is not alone. The vacuum froths with virtual pairs, electrons and positrons flickering into existence and vanishing, borrowed from nothing and repaid. Near a real electron, those virtual pairs line up. The positrons, positively charged, drift slightly inward toward the electron. The virtual electrons drift outward. The bare electron ends up wrapped in a thin veil of opposite charge that partially cancels it. From far away you see a screened, weakened electron. Push in close, and you get inside the veil, and the charge you feel is larger. Physicists say the electric charge runs. At the energies of an ordinary chemistry experiment, the fine structure constant is about 1/137. At the energies reached in a collider, it climbs to about 1/128. The vacuum is a dielectric and it screens. Now put colour into that vacuum. The virtual quark and antiquark pairs screen exactly as before. But the vacuum also froths with virtual gluons, and gluons carry colour, and they do not screen. They do the opposite. They spread the colour charge outward, smearing it across a wider region, so that when you stand far away you feel more charge, not less, and when you push in close you feel less. The colour force gets weaker at short distance. It is called anti-screening, and it means the theory has the shape the Stanford data demanded. In 1973, David Gross at Princeton set his graduate student Frank Wilczek on the calculation, expecting to prove that no quantum field theory could behave this way. Gross wanted to kill the quark model, or at least the idea that quantum field theory could describe the strong force at all. Wilczek was 21. They made a sign error, got the ordinary answer, found the error, and got the extraordinary one. Hugh David Politzer, a graduate student at Harvard, did the same calculation independently and got the same result, and the 2 papers appeared back to back in the same issue of Physical Review Letters. The 3 shared the Nobel Prize in 2004. The property is called asymptotic freedom. As the distance goes to 0, the strong coupling goes to 0, and the quarks inside a proton, examined by an electron with a fast enough shutter, are essentially free particles. Bjorken's scaling was not an accident of the data. It was quantum chromodynamics being seen up close. The number that runs is called alpha strong. At the energy scale of the Z boson, it's around 1/10, weak enough that physicists can calculate with it using ordinary approximation methods, adding up small corrections. At the scale of the proton itself, roughly 1 femtometer, it is around 1. Not small. Too large to expand in, which is why the interior of the proton resisted calculation for decades, and why nobody could compute its mass with pen and paper. Read asymptotic freedom backward and it becomes a threat. If the force fades as quarks approach each other, it grows as they separate. It does not fade with distance the way every other force does. Pull a quark out of a proton, and the force pulling it back does not weaken. It stays. And what happens when a force that never weakens meets a quark that keeps going is the reason no one has ever held a quark. Stretch a rubber band between your hands and pull. The tension climbs, the band thins, and eventually it snaps, and you're left holding 2 loose ends. That is what a rubber band does, and it is nearly what the strong force does, except that the strong force has no loose ends. Here is the picture the theory gives. 2 quarks bound together are joined by a colour field, and because gluons attract gluons, that field does not fan out into the surrounding space. It collapses into a narrow tube, a flux tube, perhaps a femtometer across, running from one quark to the other. Inside the tube, the field is intense. Outside it, there is almost nothing. Because the tube has a fixed thickness, pulling the quarks apart does not spread the field thinner. It just makes a longer tube, and a longer tube holds more energy in proportion to its length, exactly the way a longer rope has more rope in it. Energy that rises steadily with distance means a force that does not fall off at all. The strength of that force can be quoted, and the number is worth sitting with. The energy in the tube climbs by roughly 1 billion electron volts for every femtometer you pull. Converted into ordinary units, that is a tension of about 160,000 newtons, which is the weight of 16 metric tons. 2 quarks, each smaller than anything we can measure, are joined by a string that pulls with the weight of a loaded truck, and it pulls that hard whether they are a femtometer apart or a meter apart. You will never pull one out. Long before you get anywhere, the energy you have poured into the tube exceeds the energy needed to make a fresh quark and antiquark from nothing, using Einstein's exchange rate between energy and mass. So the tube does the cheap thing, it breaks, and at the break a new quark and antiquark appear, one capping each raw end. You started with a proton and a quark you were trying to steal. You end with a proton and a meson, and the quark you wanted is now bound inside the meson. Pull harder, and you make more mesons. The harder you pull, the more particles you manufacture, and never once do you hold a bare quark. Cut a bar magnet in half, hoping for a lone north pole, and you get 2 magnets, each with both poles. That is the closest everyday version, and it fails in one important way. The magnet's poles were always there in the material. The quarks that cap the broken flux tube did not exist a moment earlier. They were made, on the spot, out of the energy of your pulling. This is confinement, and it is why the debris from a struck quark at Stanford came out as a spray of ordinary particles rather than as a quark. It is why there are no fractional charges in any material anyone has ever tested, and people have looked hard, including Millikan-style experiments on niobium spheres. It is also, and this deserves saying plainly, not proven. Quantum chromodynamics is believed to confine. Lattice calculations show it confining. No one has ever derived confinement from the equations in a rigorous mathematical sense, and the problem of doing so carries a $1 million prize. Now hold both facts at once. The quarks inside a proton are so lightly held, at short range, that they behave as free, and the field that holds them stores an enormous amount of energy that grows without limit, energy that can be converted into matter at the slightest provocation. That field is inside you, and it is the reason a proton weighs what it does. Take the proton apart on paper and count what is there. 2 up quarks and 1 down quark. The up quark's mass is about 2 million electron volts, in the units particle physicists use, where the electron itself is about 500,000. The down quark is about 4.5 million. Add the 3 and you get roughly 9 million electron volts. The proton's mass is 938 million electron volts. The quarks supply about 1%. The number is not in dispute and has been known for decades, and it is the plainest statement of what this whole story is about. 99% of the proton is not made of anything with mass. What else is in there? Gluons, which have no mass at all, and a great many of them. Quark and antiquark pairs flickering into and out of existence, borrowed from the vacuum and repaid, most of them lasting for a time too short to state usefully. And the colour field itself, twisted into flux tubes, snapping and reforming in a state of permanent violence. The 3 quarks in the standard picture are called valence quarks, borrowing a word from chemistry. They are not 3 things sitting in a bag, they are the net excess, the leftover after every quark has been matched against an antiquark and cancelled. Reach into a proton and grab a quark, and it is overwhelmingly likely to be a member of some pair that will vanish before you can turn around. Only on balance, only in the accounting are there 3. So the proton is mostly not matter, in the sense you mean the word. It is field. It is energy, in motion, confined to a sphere about 0.8 of a femtometer across, and that energy has nowhere to go because the colour force will not let it leave. Try to feel the scale of what is happening in there. The quarks inside a proton move at speeds approaching light. The gluon field they generate changes state on a timescale of roughly 10 to the minus 24 seconds. In the time light takes to cross a single atom, the proton's interior has rearranged itself thousands of times. It has never once been still, not in the 14 billion years since it formed, not for an instant. That is the storm. Not a metaphor for something calmer that is really going on underneath. The storm is the thing, and it settles a confusion that trips almost everyone the first time. People say the proton is mostly empty space, in the way an atom is mostly empty space. The atom genuinely is. Electrons are far from the nucleus, and there is nothing between them worth mentioning. The proton is the opposite. There is no emptiness inside the proton. Every point in it is filled with field, energetic, roiling, and the tiny hard quarks that our diagrams draw as the real occupants are by mass, a rounding error on the vacuum they swim in. The everyday intuition, the one that says heavy things are heavy because they contain heavy things, has now failed completely. It failed quietly, in a calculation, with no drama at all. Something has to replace it. The replacement was written down in 1905 by a patent clerk in Bern, in a 3-page afterthought to a paper he had already published that year, and almost nobody at the time understood what it would eventually mean. Energy and mass are the same thing. A sealed box with mirrored walls, holding nothing but light. The photons inside have no mass, not a trace of it, and they bounce off the walls forever. Put that box on a scale. It weighs more than the empty box did, and the extra weight is exactly the energy of the light divided by the speed of light squared. That is Albert Einstein's relation, and most people meet it in the direction that makes bombs. Mass can be converted into energy, and a small amount of mass yields a terrifying amount. But the equation is an equal sign, and it reads just as well from the other side. Energy is mass. Anything with energy, trapped, weighs. The proton is that box. The light inside is the gluon field, and the walls are the confinement of the colour force, which will not let any of it out. Take the numbers seriously for a moment. The quarks inside carry kinetic energy, moving at nearly the speed of light in a space 0.8 of a femtometer wide. The gluon field between them stores the energy of its own tension. Add the motion, and the field, and the flickering of virtual pairs, divide by the speed of light squared, and you have almost the whole of the proton's mass. About 99% of what you feel when you lift anything is confined energy, weighed on a scale. Then there is the last 1%, and it comes from somewhere else entirely. The up and down quarks do have small masses of their own, and those masses have nothing to do with the strong force. They come from the Higgs field, an entity that fills all of space evenly, at every point, including the space inside your body and the vacuum between galaxies. Particles that interact with it are slowed by that interaction, resisting acceleration, and resisting acceleration is what mass is. The electron gets its mass this way. So do the quarks, each in proportion to how strongly it couples. Peter Higgs, a soft-spoken Edinburgh theorist who once said the modern academic system would never have employed him because he was not productive enough, wrote his paper in 1964. François Englert and Robert Brute in Brussels published the same idea weeks earlier. It took 48 years and a machine 27 kilometres around to find the particle that proves the field is there, and in July of 2012, 2 teams at the Large Hadron Collider announced it. Higgs, sitting in the audience, wept. So there is a popular sentence that goes, "The Higgs field gives things their mass." It is true, and it is badly misleading. The Higgs gives mass to the elementary particles. It supplies the electron's mass entirely, and the top quarks, and the up and down quarks too. And the up and down quarks are 1% of you. If you switch the Higgs field off tomorrow, atoms would fall apart because massless electrons would fly away at the speed of light. But the proton would still weigh nearly what it weighs now. The mass in your hand, the mass of the water in the glass, is nearly all of it a consequence of quarks being trapped, not of quarks being heavy. Frank Wilczek called this mass without mass. The bulk of the substance of ordinary matter comes from the energy of confinement, from a field so tightly bound to itself that it cannot escape, converted into weight by the exchange rate Einstein wrote down as an afterthought in a 3-page paper in 1905. This is a lovely story, and stories are cheap. The claim is a number, 93.8 in units of 1,000,000 electron volts, and the quarks give 9. Nobody had ever calculated that number from the equations of quantum chromodynamics, because at the proton scale the force is too strong for the usual methods, where you add up small corrections and stop. To check it, physicists had to give up pen and paper, chop space-time into a grid, and build the proton inside a computer. Kenneth Wilson had a habit of taking problems apart from the bottom. He had come up through Caltech and Harvard. He would win the Nobel Prize for understanding phase transitions, and he was one of the first physicists to argue that computing was not a service industry for theory, but a way of doing theory. In 1974, he proposed something that sounds like vandalism: replace continuous space-time with a lattice, a cubic grid of points, spaced perhaps 1/10 of a femtometer apart. Put the quarks on the grid points, put the gluon fields on the links between them. Then, instead of solving the equations, evaluate the quantum theory the way it is actually defined, as a sum over every possible history of the field, weighted by how likely each history is. The number of histories is beyond counting, so you sample them, the way a pollster samples voters. Generate field configurations at random, weighted correctly, tens of thousands of them, and average. This is Monte Carlo sampling, named for the casino, and it is the same technique used to price options and model neutron diffusion. The cost is brutal. Each configuration is a set of numbers on every link of a 4-dimensional grid, and a modest lattice might be 32 points on a side in space, and 64 in time, which is more than 2 million points and 8 million links, each carrying a matrix. Generating one configuration requires inverting enormous sparse matrices over and over. The calculations run for months on some of the largest machines in the world, and lattice groups have historically built their own hardware when the market would not give them what they needed. Then there are the compromises. The lattice spacing is not 0, so you run at several spacings and extrapolate to 0. The box is not infinite, so you run at several sizes and extrapolate. And for many years, the up and down quarks were given masses far heavier than the real ones, because light quarks make the matrix inversions catastrophically slow, and the results were extrapolated down to reality with a theoretical crutch. By the middle of the 2000s, the machines and the algorithms had caught up. In 2008, a collaboration spread across Wuppertal, Budapest and Marseille, led by Zoltán Fodor and with Stefan Dürr as first author, published a calculation in Science. They computed the masses of the proton, the neutron, and a set of other hadrons from the equations of quantum chromodynamics, with essentially nothing put in by hand except the quark masses and one overall scale. The proton came out right, to within a couple of percent. Sit with what that means. Starting from a theory of coloured quarks and self-interacting gluons, written down on the basis of jets and scattering and a symmetry argument, a computer produced the weight of the thing in your hand. The mass of ordinary matter calculated. Not fitted, calculated. The lattice can do more than weigh. It can be interrogated. Ask where the energy sits inside a proton, and the answer that comes back is that the largest single share is the gluon field, followed by the kinetic energy of the quarks, with the quark masses contributing that small fixed slice. Different groups slice the accounting slightly differently, since the pieces are not separately measurable, but every slicing agrees on the headline. The proton is a knot of field energy. The lattice also shows the flux tube directly. Place a quark and an antiquark on the grid, separate them, and map the energy density in between. It does not spread. It forms a narrow chord, and when you look closely at what the lattice's proton contains at any given instant, the 3 valence quarks are the smallest part of the crowd. The rest of the crowd is a sea. Reach into the proton and pull out a quark, and ask what kind it is. You expect 2 chances in 3 of an up and 1 in 3 of a down, because that is what a proton is made of. That is not what you find. You find ups and downs and anti-ups and anti-downs, and strange quarks and anti-strange quarks, and if you look hard enough, charm. The gluon field is not passive. A gluon carries energy, and energy in this theory can become matter without asking permission. A gluon splits into a quark and its antiquark, which live for a moment and annihilate back into a gluon. Another split somewhere else. At any instant, there is a population of these pairs inside the proton, boiling up and disappearing, and the population is large. Physicists call it the sea, and it is not a poetic name so much as a technical one, appearing in the equations alongside the valence quarks. C quarks come in pairs, always. A C-up quark has a matching anti-up somewhere, so the accounting still works. Count all the ups, subtract all the anti-ups, and the answer is 2. Count downs minus anti-downs, and the answer is 1. The proton's identity, its charge and its quantum numbers, is a difference, not a census. The deep inelastic scattering experiments see the sea clearly, because a struck antiquark scatters an electron just as a quark does. What decides which you hit is the momentum fraction, that variable x from Feynman's picture. Look at the proton at high x, where a single parton carries most of the momentum, and you find valence quarks, the 3 that give the proton its name. Look at low x, at partons carrying 1,000th of the proton's momentum, and the valence quarks are nowhere. There the proton is a swarm of C quarks, and above all of gluons, numbering in the hundreds and rising as you look lower. Most of the objects inside a proton are gluons, and most of them are soft. There is a distinction here worth being careful about, because the language misleads. The sea is not a substance sitting inside a container. Nothing is there in the way a marble is in a bag. The sea is what the field does. It is the vacuum of quantum chromodynamics fluctuating, and it fluctuates whether or not a proton is present. What the proton does is confine a region of that fluctuating vacuum and give it a shape. By the 1980s, everyone expected the sea to be simple. Gluons split into quark pairs, and gluons are blind to flavour. A gluon has no preference for up over down. It sees only colour and mass, and the up and down quarks have nearly the same mass, differing by an amount too small to matter here. So the sea should be even-handed, as many anti-up quarks as anti-down quarks, to a fraction of a percent. This was not a wild guess. It was the direct prediction of the mechanism everyone believed in, and it had a name in the equations, a statement called the Gottfried sum rule, which tied the difference between the protons and the neutron structure to that symmetry. In 1991, a group at CERN measured the sum rule and got the wrong answer. Whatever the sea was doing, it was not doing the simple thing. 2 experiments in Illinois spent the next 30 years finding out how badly. The new muon collaboration at CERN scattered muons off hydrogen and deuterium and measured the difference between how a proton and a neutron respond. The Gottfried sum rule said that difference should come to 1/3. They measured about 2/10. The discrepancy had one obvious reading. The proton contains more anti-down quarks than anti-up quarks. The sea is lopsided. To confirm it directly, physicists used a process discovered by Sidney Drell and Tungmo Yan. Fire protons at a target. Sometimes a quark from the beam annihilates an antiquark from the target, producing a virtual photon that becomes a muon and an antimuon flying out. Those muons are easy to catch and their energies tell you which antiquark was destroyed. Compare a hydrogen target made of protons with a deuterium target, which adds neutrons, and the ratio isolates the anti-down to anti-up ratio inside the nucleon. Experiment 866 at Fermilab, called Nucia, ran in the late 1990s. The answer came back clear. Around a momentum fraction of 1/10, there were roughly 1.5 times as many anti-down quarks as anti-up quarks. Then, at higher x, the ratio appeared to fall, and in the last data points it dipped below 1, suggesting the imbalance reversed. Those last points had large uncertainties and nobody knew whether to believe them. It took 20 years to check. A follow-up, Experiment 906 called Sequest, used a lower beam energy to reach that higher region cleanly, running from 2012. Its result, published in Nature in 2021, found no reversal. The anti-down excess persists, holding steady out to a momentum fraction of nearly 1/2. So the proton carries a permanent flavor asymmetry in its sea, and gluon splitting cannot make one. Where does it come from? The best explanation is old and slightly embarrassing because it is Yukawa's pions again. A proton can, for an instant, fluctuate into a neutron with a positive pion orbiting it, borrowing the energy and paying it back. That positive pion is made of an up quark and an anti-down quark. The proton can also fluctuate into a neutron-like state with other pions, but the arithmetic of the possibilities favours configurations rich in anti-down. Fluctuate often enough, and an outside probe averaging over the fluctuation sees an excess of anti-down quarks. The proton spends part of its life being something else, and the something else leaves a fingerprint. There is a nice tension in this. Pions are made of quarks, and quarks live inside the proton, and yet the clearest way to explain a feature of the proton's quark content is to say the proton is sometimes a neutron with a pion around it. Both descriptions are correct. They are the same physics counted in different currencies, one in quarks and gluons, one in the composite particles those quarks assemble into. Neither is more real. The theory permits both books to be kept, and it is a working physicist's skill to know which book to open. What the asymmetry establishes, plainly, is that the proton's contents are not derivable from 3 quarks, plus a mechanical rule. The interior has structure that nobody guessed, discovered only by measurement, and there is no reason to think this was the last such surprise. Indeed, there is another, and it concerns a quark so heavy that a proton should not be able to hold it at all. The charm quark weighs about 1.25 billion electron volts. The proton weighs 938 million. The quark is heavier than the particle. Whatever else is inside a proton, a charm quark ought not to be, in any permanent sense. And yet in scattering experiments, charm quarks show up inside protons routinely. That much is not mysterious. Hit the proton hard enough, and the energy you deliver can create a charm and anti-charm pair out of a gluon on the spot. The charm you see was made by your own probe, in the instant of collision. Physicists call this extrinsic charm, and it is exactly what the theory expects. The question that has stayed open since 1980 is whether there is any other kind. Stanley Brodsky, working with Paul Hoyer, Chris Peterson, and Neil Sakai, argued that quantum mechanics permits a proton to fluctuate briefly into a 5-quark state, the usual 2 ups and a down plus a charm and an anti-charm. The energy needed is borrowed and returned quickly, which the uncertainty principle allows. If the proton spends even a small fraction of its life in that configuration, then charm is part of the proton's own wave function, present before any probe arrives. They called it intrinsic charm. It makes a distinctive prediction. Extrinsic charm, created from a splitting gluon, is soft, carrying a tiny share of the proton's momentum. Intrinsic charm has to be fast. In the 5-quark state, the quarks share momentum roughly in proportion to their masses, so the heavy charm quark carries a large slice, and it should appear at high x, where nothing else expects it. For 40 years the evidence sat in that awkward middle where a signal is neither present nor absent. Some analyses of high-energy proton collisions preferred a little intrinsic charm. Others were consistent with none. The measurements that mattered were difficult. The theoretical uncertainties large. In 2022, the NNPDF collaboration published in Nature a global analysis of an enormous body of scattering data and reported evidence for intrinsic charm at about 3 standard deviations, carrying on the order of 0.5% of the proton's momentum, concentrated at high x, as Brodsky's picture demanded. 3 standard deviations is not a discovery. Particle physics conventionally requires 5, and it has good reason. 3 sigma effects have vanished before. Some groups reading the same data have argued the significance is overstated, that it leans on assumptions about how quark distributions are parameterized. The matter is not settled, and the honest position is that intrinsic charm is likely and not certain. What it would mean, if it holds, is worth stating carefully. It does not mean the proton contains a charm quark the way a wallet contains a coin. It means that the proton, as a quantum object, is a superposition of configurations, and that one of those configurations occupied a small fraction of the time includes a charm and an anti-charm. The proton is not a fixed inventory. It is a probability distribution over inventories, and heavy things sit far out on the tail of it. This is a strange thing to be true about the object that constitutes your body, and it points at something stranger, which the last several chapters have been circling. The proton does not have a definite list of contents at all. What it appears to contain depends on how hard you look, and that is not a limitation of the instruments, it is the physics. The word contains is doing quiet damage. In ordinary speech, a box contains what is in it, and the answer does not change with the strength of your flashlight. Take a photograph of the proton with a soft probe, one that cannot resolve anything smaller than a proton, and the proton is a single object with no parts. Turn up the resolution, meaning strike it with a more energetic electron carrying a shorter wavelength, and 3 quarks appear. Turn it up further and each quark is surrounded by gluons it has radiated. Further still, and each of those gluons is split into quark pairs, and those pairs radiate their own gluons. There is no bottom to this. The number of things inside a proton grows without limit as the resolution increases, and it grows fastest for the gluons at small momentum fraction, whose numbers climb steeply. The equations that describe how the picture changes with resolution were written down in the mid-1970s in Moscow and in Rome. Vladimir Gribov and Lev Lipatov worked on them in Leningrad, Yuri Dokshitzer independently, and Guido Altarelli and Giorgio Parisi in Italy, and everyone now calls the result by their initials. The equations do not tell you what the proton contains. They tell you how the contents at one resolution follow from the contents at another, measure at one scale, evolve, predict at every other. That is a peculiar kind of theory, and it is enormously successful. It is checked constantly at the Large Hadron Collider, where the prediction of any collision rate depends on knowing what the proton looks like at that energy. The most direct test came from Hera in Hamburg, the only machine ever built to collide electrons with protons head-on, running from 1992 to 2007. It could reach far smaller momentum fractions than anything before it, and it found that Bjorken's scaling, the clean result that had launched the whole quark picture, is violated in exactly the way the evolution equations require. At small x, the number of gluons rises steeply as you look harder, and the curves shift, and they shift by the predicted amount, which is a lovely thing. The theory's first triumph was that scaling held. Its second triumph was explaining precisely how much scaling fails. The rising gluon count cannot continue forever. If the number of gluons inside a proton grows without bound, then at some point the proton's face becomes so crowded with them that they begin to overlap and recombine, gluon fusing with gluon, and the growth must slow. That state, a proton so densely packed with soft gluons that they saturate, has a name, the color glass condensate, and it may be the universal form all matter takes when viewed at high enough energy. Nobody has cleanly observed it. Hera saw hints of the taming. The Large Hadron Collider sees suggestive behavior in collisions with lead nuclei, where the effect should be amplified because a heavy nucleus packs many protons worth of gluons behind one another. It is one of the reasons for the machine now under construction on Long Island. So the proton has no fixed contents, its mass is field energy, and its interior boils. There remains one property that seemed safe. The proton spins in a fixed and simple amount, and everyone knew where that came from. They were wrong, and the way they found out was an accident. Spin is a property particles carry the way they carry charge. An electron has spin 1/2, so does a quark, so does a proton, and it is not a small technical fact. The proton's spin is why magnetic resonance imaging works. Put a body in a strong magnetic field, and the protons in its water molecules align, and radio waves flip them, and the flipping is what the machine listens to. Every MRI scan is a measurement of proton spin, taken a trillion times over. Where does that spin come from? The obvious answer, for 20 years, was the quarks. 2 ups and a down, each with spin 1/2. Point 2 of them up and 1 down, and the halves add to 1/2. The arithmetic is clean, and it predicts the proton's magnetic moment approximately right, which seemed like confirmation. To test it, you need a beam whose particles all spin the same way, and a target whose protons all spin the same way, and then you count how the scattering rate changes when you flip one of them. This is hard. Polarizing a target means cooling frozen ammonia to a fraction of a degree above absolute zero, sitting it in a powerful magnetic field, and pumping microwaves into it for hours to line up the protons. The European muon collaboration did it at CERN in the middle 1980s, firing a polarized muon beam into a polarized target. The physicists expected to confirm a settled number and go home. Their result, published in 1988 in a paper with Jack Ashman as lead author, said that the spins of the quarks account for very little of the proton's spin. The measurement was consistent within its errors, with the quarks contributing nothing at all. The reaction was disbelief, then a decade of harder measurements at CERN, at Stanford, at the German electron synchrotron. The number moved, as numbers do when the systematics improve. The current value is that the quark spins, valence and C together, supply somewhere around 30% of the proton spin, not 0, not 1. 70% is missing, and the newspapers of the time called it the spin crisis, which was overstated. The crisis was in the model, not the theory. Nothing in quantum chromodynamics ever promised that the quarks would carry the spin. Consider what else is in there. Gluons have spin 1. If the gluons inside the proton preferentially spin along with it, they add, and everything inside is moving, orbiting, swirling. A quark circling the proton's center carries orbital angular momentum, exactly as the Earth's orbit carries angular momentum distinct from its rotation. That orbital motion contributes too, so the budget has 4 entries: quark spin, gluon spin, quark orbital motion, gluon orbital motion. They must sum to 1/2, and only the first was ever measured with confidence. There is a further wrinkle that makes it genuinely subtle rather than merely difficult. Separating the gluon spin from its orbital motion is not obviously a well-defined operation in a theory like this one, and physicists have argued for years about which decomposition is the physical one. Xiangdong Ji proposed one scheme, Elliott Leader and Cedric Losset have written at length about the ambiguities, and the argument is not closed. But the gluon spin at least is measurable, and to measure it you need to collide 2 beams of protons, both of them spinning the same way, which had never been done. Brookhaven National Laboratory sits on Long Island, on land that was once an army camp. Beneath it runs a ring 3.8 kilometers around, the relativistic heavy ion collider, built in the 1990s to smash gold nuclei together. It has a second capability, unique in the world. It can accelerate protons while preserving their spin direction, using devices called Siberian snakes that flip the spin at intervals to keep small imperfections in the magnets from ruining the alignment. Collide 2 spin-aligned protons and the gluons inside them meet. Look at what comes out, at jets, or at particles called neutral pions, and compare the rate when the beams spin the same way against when they spin oppositely. A gluon that prefers to spin along with its proton will produce a small asymmetry, a % or less. The Phoenix and Star experiments measured it through the 2000s. For years, the answer hovered near 0, and the missing spin looked as though it might be missing everywhere. Then, in 2014, with better data reaching smaller momentum fractions, an asymmetry emerged. The gluons carry positive spin, and the current estimate is that they supply perhaps 20 to 40% of the protons total. though the fraction depends on how far down in momentum you're willing to extrapolate, and much of the gluon population sits below where anyone has measured. Take the quark spin at around 30% and the gluon spin at something like a third, and you are near the total but nowhere near certain of it. What remains, and it may be substantial, is orbital angular momentum. The quarks and gluons inside the proton are not merely spinning, they are going around. This is where matters stand, and it is worth saying it as plainly as it deserves. Nobody has ever measured the orbital angular momentum of the quarks inside a proton. There is a theoretical route to it, through objects called generalized Proton distributions, which encode not just how much momentum a quark carries, but where in the proton it sits while carrying it. Measuring them requires a process where an electron strikes a proton, the proton survives intact, and a single high-energy photon comes out. It is called deeply virtual Compton scattering. The rate is small, and the interpretation demands a great deal of theory. So the proton spin, the property that a hospital scanner relies on every day, has not been accounted for. We know its value exactly, 1/2. We cannot yet say where it comes from. It is a good illustration of what this subject is like. The strong force is not a theory with gaps in it. Quantum chromodynamics has passed every test that could be arranged, at every energy anyone has reached for 50 years. What it lacks is not correctness but tractability. We possess the equations that govern the proton's interior, and we cannot solve them, and so the object nearest to hand, the thing your body is built from by the trillion, keeps its accounts hidden. And when physicists went to measure something as simple as the proton's size, expecting a routine improvement, the number changed. The proton is not a point, and it has a size, and measuring that size is the kind of task that gets handed to graduate students. Two methods existed, and for decades they agreed. The first is scattering. Fire electrons at hydrogen, watch how they deflect at small angles, and the deviation from what a point charge would do tells you how the proton's charge is spread out. The second is spectroscopy. The electron in a hydrogen atom spends a tiny fraction of its time inside the proton, and while it is there, the electrical pull on it is slightly less than a point charge would give. That shifts the atom's energy levels by an almost unmeasurably small amount, and hydrogen's levels have been measured with an accuracy that borders on the absurd to more than a dozen digits. Both methods gave a charge radius near 879 thousandths of a femtometer, with an uncertainty in the last digit or two. Settled. Randolph Pohl, at the Max Planck Institute of Quantum Optics, wanted to do better. His idea was to build a strange atom. Replace hydrogen's electron with a muon, that heavy cousin from the cosmic ray plates, 200 times heavier and otherwise identical in the way it feels electricity. A heavier particle orbits closer. The muon in muonic hydrogen spends far more of its time inside the proton, so the energy shift due to the proton size is larger by a factor of about 8 million. What was a whisper in ordinary hydrogen becomes a shout. Muons live for 2 millionths of a second. The experiment at the Paul Scherrer Institute in Switzerland had to make monic hydrogen, fire a laser at it, and read the result before the atoms fell apart. It took years of failed runs. In 2009, in the small hours of a morning shift, the signal appeared. The radius came out at 842 thousandths of a femtometer, 4% smaller than the accepted value, and, because the monic measurement was so precise, wrong by 7 standard deviations. Published in Nature in 2010, it was called the Proton Radius Puzzle, and it was serious. Either one of the measurements had a mistake nobody could find, or the muon does not interact with the proton the same way the electron does, which would break a symmetry called lepton universality and open a hole in the standard model. Papers proposed new forces coupling only to muons. Others went back through the electron scattering analyses, hunting for a subtle bias in how the data were extrapolated to zero deflection angle, since the radius is read off from a slope at a place you cannot actually measure. The resolution came slowly and unglamorously. In 2017, a group in Garching remeasured ordinary hydrogen spectroscopy and found the small value. In 2019, another group in Toronto did too, and the Pratt experiment at Jefferson Laboratory in Virginia, an electron scattering measurement designed to reach unusually small angles, also landed near 831 thousandths. The muon was innocent. The older electron experiments, most of them, had underestimated their systematic errors. Not all measurements agree even now, and the world average has shifted downward to about 841 thousandths of a femtometer. There is no new physics here, and the story is worth telling anyway. A discrepancy that looked like a crack in the standard model turned out to be a lesson about error bars, which is the more common ending and the less reported one. What survives is the number. 841 thousandths of a femtometer, the distance across which all of that confined energy is held. And once you can measure how charge is distributed inside the proton, you can ask a question that sounds like it belongs to engineering rather than particle physics. If there is a field in there under enormous tension, held in by a force that will not let it out, then the interior of the proton must be under pressure. Volker Burkert, Latifa Elouadrhiri, and François-Xavier Girod worked at Jefferson Laboratory, where a beam of electrons runs around a racetrack buried under a Virginia field. In 2018, they published a paper in Nature, reporting a measurement nobody had thought was possible. They had measured the pressure inside a proton. The route to it is indirect and clever. Every object has a way of responding to being squeezed and sheared, and in a relativistic quantum theory that response is encoded in something called the energy-momentum tensor, the same mathematical object that tells gravity how much to bend around a mass. For a proton, one of its pieces describes the internal distribution of pressure. Gravity is far too weak to probe a proton, so the tensor seemed forever out of reach. Shangdong-Ji showed in the 1990s that the same information hides in the generalized parton distributions, which can be reached with light. Maxim Polyakov worked out how the pressure specifically could be extracted. The measurement is deeply virtual Compton scattering, the process mentioned earlier. An electron strikes a proton, the proton survives, and a single energetic photon comes out. Catch enough of those at many beam energies, and you can reconstruct the tensor's shape. Burkert's group used 20 years of accumulated data from the class detector. The result is a curve of pressure against distance from the proton's center. Near the middle, out to about half a femtometer, the pressure is positive and enormous, pushing outward. Beyond that it turns negative, pulling inward, holding the whole thing together, and the inward and outward parts balance exactly, as they must for a stable object. The number at the center is where the story became newspaper copy, roughly 10 to the 35th pascals. That is about 10 billion trillion times atmospheric pressure. It exceeds, by an order of magnitude or so, the pressure estimated at the heart of a neutron star, which is the densest matter in the observable universe outside a black hole. The most intense pressure known to physics is inside every proton in your hand, and it always has been, and it does nothing at all. There is no explosion because the outward push at the core is precisely cancelled by the inward pull of the confining field at the edge, a balance the strong force enforces without effort. The caveats deserve stating. The measurement carried substantial uncertainties, perhaps 30% or more, and the extraction leans on assumptions about the shape of the distributions. It was a first look, not a precision result, and later analyses have adjusted the numbers. What was not in doubt was that a quantity everyone had filed under permanently unmeasurable had been measured at all. Think about what that pressure is. It is not the quarks bouncing off each other like gas molecules. It is the gluon field, wound tight, straining against confinement. The proton is a container holding a substance under greater pressure than a collapsed star, and the container is made of the same substance. Here is the thing about a system in balance that tight. Change its surroundings, even slightly, and the balance shifts. A proton alone in empty space and a proton pressed against other protons inside a nucleus are not quite in the same situation. For a long time, nobody thought that could matter. The strong force inside a nucleus was supposed to be a gentle residual thing, pion exchange, far too weak to reach down and disturb the quarks. Then a group at CERN scattered muons off iron and off deuterium, expecting no difference beyond simple counting, and found one. Nuclear physics and particle physics were separate trades. One studied protons and neutrons sticking together at energies of a few million electron volts. The other studied what was inside them at energies 1,000 times higher. The dividing assumption was that a proton is a proton. Bind it into a nucleus, and its quarks would not notice, because the binding energy per nucleon in iron is about 8 million electron volts, and the energy scale of the proton's interior is 1,000 million. 8 parts in 1,000. Nothing. The European Muon Collaboration, the same group that would later find the spin crisis, was measuring the quark structure of iron in 1982. Iron was chosen for a mundane reason. It makes a convenient target. They compared it to deuterium, which is 1 proton and 1 neutron barely bound together, standing in for free nucleons. The ratio should have been flat, 1 at every momentum fraction. It was not. At high X, the quarks inside iron carried less momentum than the quarks inside deuterium. At middling X, around a third, the deficit reached perhaps 15%. At low X, there was a rise. The paper is credited to Jim Aubert and the collaboration, and the effect took the name of the group, the EMC effect. Emilio Segre's textbook had said, in effect, that this could not happen. It happened. More than 1,000 papers have been written about it. There is still no agreed explanation. The candidates fall into 2 families. In the first, every proton in the nucleus is slightly altered by its neighbours, swollen a few %, its quarks given a little more room, and therefore a little less momentum each. The proton, on this view, is a soft object that deforms when packed. In the second family, most protons in the nucleus are completely ordinary, and the effect comes entirely from a small minority that happen, at any instant, to be in short-range correlated pairs. A proton and a neutron approach each other closely, within a fraction of a femtometer, their surfaces overlapping, and for that moment the two are a single 6-quark object with quite different structure. Perhaps 20% of nucleons are in such pairs at any time. The rest are untouched. The second picture has evidence behind it. Experiments at Jefferson Laboratory, led in part by Orhen and Douglas Hiesin-Botham, found that the size of the EMC effect in a given nucleus tracks the number of short-range correlated pairs in it, across nuclei from helium to lead. 2 effects that should be unrelated march together. That is suggestive rather than conclusive. The correlation could have a common cause, and some theorists argue the mean field picture can be tuned to fit as well. Set aside which explanation wins and look at the bare fact. Put a proton next to another nucleon, and its internal quark structure changes measurably. The interior of the proton is not sealed. It responds to the world outside its boundary, at a scale where nobody thought the outside world had any leverage. Which raises a question that turns the whole subject around. If neighbours change a proton, what happens when there are no boundaries at all? Heat a lump of protons and neutrons hot enough, squeeze them close enough, and their edges cease to mean anything. Bring water to a boil and the molecules do not change. They only stop holding on to one another. Every phase transition in ordinary life works this way, and the strong force has one too, and it does something that ordinary boiling does not. It dissolves the containers. Heat nuclear matter past roughly 2 trillion degrees, or squeeze it past a few times nuclear density, and the protons and neutrons overlap so thoroughly that no quark can say which nucleon it belongs to. Confinement, which never releases a quark into empty space, releases it into a medium already full of quarks. The result is a soup of quarks and gluons, free to travel across distances far larger than a proton. It is called the quark-gluon plasma. You make it by colliding heavy nuclei. Gold on gold at Brookhaven's relativistic heavy ion, collider from 2000, lead on lead at the Large Hadron Collider from 2010. 2 nuclei, each flattened by relativity into a disk, pass through one another, and in the region they overlap the energy density for a moment exceeds anything else in the present universe. The plasma lives for about 10 to the minus 23 seconds, and then cools and freezes back into ordinary hadrons, which is all the detectors ever see. Everything known about it is reconstructed from the debris. The first surprise was that it is a liquid. Theorists had expected a gas, a thin swarm of quarks bouncing around freely, because at those energies asymptotic freedom says the coupling is weak. Instead, the matter produced at Brookhaven flowed. When two nuclei collide slightly off-centre, the overlap region is almond-shaped, and pressure gradients push harder along the short axis than the long one, so the debris comes out with a characteristic pattern called elliptic flow. Seeing that pattern means the medium behaved collectively, like a fluid, before it broke apart. More than a fluid. It is the most perfect fluid known, meaning it has almost no viscosity, almost no internal friction. Its ratio of viscosity to entropy density approaches a bound that string theory calculations suggest may be fundamental. Liquid helium at a fraction of a degree above absolute zero is far more viscous by this measure. The stuff that fills a heavy ion collision is 100 times hotter than the centre of the Sun and flows more smoothly than any liquid in a laboratory. A second probe, jet quenching. When two quarks scatter hard inside the collision and try to fly out back to back, one may exit near the surface while the other must cross the whole plasma. The one that crosses loses energy to the medium and emerges as a weakened jet, or none at all. Detectors at the Large Hadron Collider routinely record events with a strong jet on one side and almost nothing opposite it. The plasma swallowed it. The temperature has been measured around 2 trillion degrees Kelvin at the moment of formation, more than 100,000 times the core of the Sun. It is the hottest matter ever made by human beings. And here the story runs backward. If enough heat unbinds the proton, then early enough in the universe, when everything was that hot, no proton could exist. The matter you're made of had not yet been assembled, and the quarks that would become you were loose, roaming freely in a plasma filling all of space. There was a moment when that ended. Run the expansion of the universe backward and the temperature climbs. At 1 second after the beginning, the universe was a few billion degrees. At 1 microsecond, it was 2 trillion. That is the number from the collider. So for the first millionth of a second of the universe, there were no protons anywhere. There were quarks and antiquarks and gluons, filling every cubic centimetre of a space that was expanding at a rate that beggars description, and there was nothing they could bind into because any bound state would be shaken apart instantly. Physicists call the moment it ended the QCD phase transition, or hadronization, and it happened everywhere at once, about 10 millionths of a second after the beginning. The universe cooled through the critical temperature. The coupling grew, the flux tubes could form and hold, and every quark in the cosmos was captured permanently into a colourless bundle, 3 at a time or in quark-antiquark pairs. Every proton that exists was made then. Every proton in your bones has been a proton since the universe was younger than a heartbeat, and it has never once been anything else. The lattice calculations say this was not a sudden violent transition like water freezing, with bubbles and interfaces and boundaries. At the very low net quark density of the early universe, it appears to have been a smooth crossover. The plasma thickened into hadrons gradually, the way fog becomes mist becomes dew, with no sharp line to cross. There is a debt to settle here, and it is embarrassing. Quarks and antiquarks were made in equal numbers, or nearly so. When the universe cooled, almost all of them found each other and annihilated into light. What survived to make protons was the excess, and the excess was tiny. For every billion antiquarks, there were about 1,000,000,001 quarks. Everything you can see, every star and planet and person, is that one part in 1,000,000,000 left over after the annihilation. Why there was an excess at all is unknown. Andrei Sakharov, the Soviet physicist better known in the West for his dissent, laid out in 1967 the 3 conditions any explanation must satisfy. The laws must violate the conservation of baryon number, so that a quark can be made without an antiquark. They must treat matter and antimatter differently. And the universe must fall out of thermal equilibrium while it happens. The Standard Model satisfies all three, technically, and by amounts far too small to give the excess we have. Something is missing. Notice the strangeness of what we're standing on. The strong force does not violate baryon number. Nothing in the Standard Model does, in any process anyone can observe. The number of protons plus neutrons in the universe, minus their antiparticles, has been fixed since that first microsecond. It is one of the most rigorously conserved quantities we know of, and it must have been violated once, or we would not be here. Which invites the obvious question, the one that pulls this whole story toward its edge. If baryon number was violated in the early universe, it is not a true law of nature. It is an accident of the low energies we live at. And if it is not a law, then the proton, which is the lightest particle carrying baryon number, and therefore has nothing lighter to decay into except by breaking that rule, is not necessarily stable. The proton might die. Nothing in the Standard Model kills a proton. It is the lightest baryon, and baryon number is conserved in every interaction the theory describes, so there is nowhere for it to go. That is not a deep reason. It is a restatement of the rule. In the 1970s, Howard Georgi and Sheldon Glashow noticed something at Harvard. The three forces of the Standard Model have strengths that change with energy, the strong one weakening as energy rises, the electromagnetic and weak ones strengthening. Extrapolate them upward, and the three curves nearly meet at an energy around 10 to the 16th billion electron volts. Not exactly, but close enough to suggest that at that scale the three are one force, and that our three are its low-energy shards. Georgi has said the idea came to him in an evening, and that he then realised what it implied and was briefly appalled. A unified force does not distinguish quarks from electrons. It has carriers that turn one into the other, which means a quark inside a proton can turn into a positron. The proton decays. The standard channel is a proton becoming a neutral pion and a positron. The pion decays to photons, the positron finds an electron and annihilates. The baryon vanishes, and nothing is left but light. The rate is small, because the carriers of the unified force are unimaginably heavy, and the heavier the carrier, the more suppressed the process. Georgi and Glashow's original model predicted a proton lifetime around 10 to the 30th years, which sounds untestable and is not. Watch enough protons and you do not need to wait. 1,000 tons of water holds enough protons that if the lifetime were 10 to the 30th years, you would see several decays a week. They built the detectors underground to hide from cosmic rays. IMB in a salt mine in Ohio. Kamiokande in a zinc mine under a mountain in Japan. 3,000 tons of ultra-pure water lined with photomultiplier tubes, watching for a single flash. They saw nothing. Year after year, nothing. The Georgi and Glashow model, the simplest and most beautiful version of unification, was killed by the absence of an event. Kamiokande, built to watch protons die, saw neutrinos from a supernova in 1987, and then discovered that neutrinos change flavour and therefore have mass, which won Takaaki Kajita a Nobel Prize. An experiment built for one purpose found another, which happens more often than the textbooks admit. Super Kamiokande, its successor, holds 50,000 tons of water under a kilometre of rock. It has now pushed the lifetime for the positron and pion channel beyond 10 to the 34th years. Hyper Kamiokande, under construction, will hold roughly 260,000 tons and begin taking data later this decade. Hold that lifetime against something. The universe is about 14 billion years old, which is roughly 10 to the 10th. The limit is 10 to the 34th years, 100 trillion times the age of everything. And yet a proton does not age. It has no internal clock counting down. Decay is a probability per unit time, the same in the first second as in the last, so the correct statement is not that your protons are old and tiring. It is that each one, every moment, has a vanishingly small chance of turning into light, and there are enough protons in your body that if the lifetime is near the current limit, One of them will decay while you're alive. Whether any ever do is unknown. Granunification remains an idea with no experimental support, and the proton stability may be exact. We have reached the edge of what is measured. What remains is what the machines and the mathematicians are still working on. Two unfinished things sit at the end of this story, one in a mathematics department and one on Long Island. Start with the mathematics. Quantum chromodynamics predicts that the force between quarks grows with distance and that no coloured object escapes. Lattice computers show this happening. Every experiment agrees. Nobody has proved it. The Clay Mathematics Institute in the year 2000 named 7 problems and offered $1 million for each. One of them is the Yang-Mills existence and mass gap problem. It asks for 2 things. First, show that a quantum Yang-Mills theory, of the kind quantum chromodynamics exists at all as a rigorous mathematical object in 4 dimensions. Second, prove that it has a mass gap, meaning that the lightest thing the theory can produce has a mass strictly greater than 0. The mass gap is confinement in disguise. The gluon is massless. If the theory allowed free gluons, it would produce excitations of 0 mass, and the force would reach across the room, and there would be no lightest particle with weight. Because gluons bind themselves into colourless bundles, the lightest excitation is a massive object, and the gap is the reason the strong force stops at the edge of the nucleus. The proton's mass, then, is not merely unexplained by pen and paper. It is unexplained in a way that $1 million has not fixed in 26 years. Yang, who wrote the equations in 1954, lived to see them run the world's colliders and remain unsolved. Only one of the 7 Clay problems has ever been claimed, by Grigory Perelman, who declined the money. Now, Long Island. The electron-ion collider is being built at Brookhaven, reusing the tunnel of the heavy ion machine, adding an electron accelerator so that electrons can be fired into protons and into heavy nuclei, both beams polarized, at energies and intensities beyond anything before. It was approved by the Department of Energy in 2020 and is expected to begin taking data in the middle of the next decade at a cost in the billions. It has 3 questions on its list, and you have met all of them. Where does the proton spin come from? The collider will map the gluon spin down to momentum fractions the current machines cannot reach, and measure the generalized parton distributions well enough to get at orbital motion. How is the proton's mass distributed, and what is the shape of the field inside it? Deeply virtual Compton scattering, done properly, with statistics, giving pressure and mass distributions rather than a first glimpse. And what happens when the gluon density saturates? Fire electrons at gold nuclei, where the gluons of 200 nucleons stack up behind one another, and look for the taming of the growth, the colour glass condensate, gluon fusing with gluon. There is something worth noticing in that list. Every question on it is about the thing you are made of, not about dark matter or extra dimensions or the beginning of time, about the proton, discovered by Rutherford a century ago, held in every atom, present in numbers past imagining in the water, in the glass in your hand. We can calculate its mass on a supercomputer to within 1%. We cannot say where its spin lives. We are building a machine the size of a town to find out. Pick up the glass again. The weight in your wrist is real, and now you know what it is. Almost none of it is the matter you would have pointed to. The 3 quarks that give the proton its name, the 2 ups and the down, supply about 1%. The rest is the energy of the gluon field, wound into flux tubes under a tension of 16 tons, boiling with pairs of quarks that appear and vanish, spinning, orbiting, pressed to a pressure greater than the heart of a neutron star, and held in a sphere less than a femtometer across by a force that will not let anything coloured leave. Mass is confined energy. That is the answer to the question we started with, and it is the plainest sentence in this whole story. The proton is not a bag of marbles. It is a storm that cannot escape, and its inability to escape is what you feel when you lift a glass of water. You are made of that. 10 to the 28th of these knots, roughly, one for every proton in your body, each one a region where the field of the strong force is tied up and cannot get free. Not one of them has been still since it formed. Every one of them formed in the same 10 millionths of a second, when the universe cooled through 2 trillion degrees, and every free quark in existence was captured at once and locked away forever. They have been protons ever since. They passed through the first stars and the interiors of stars that exploded, and clouds of gas that collapsed into the sun and its planets. They arrived in your body through food and water and air, and they will leave it, and they will still be protons long after there is nobody left to name them. The lightest baryon has nowhere to go. Unless the grand unified theories are right, and a quark can turn into a positron, in which case the whole thing dissolves into light after 10 to the 34th years, which is to say after a length of time that makes the age of the universe a rounding error. There is a temptation to draw a lesson from this, that matter is really energy, or that solidity is an illusion. Resist it. The glass is solid. The water is heavy. Your hand holds it. Nothing about the physics makes any of that less true, and a proton is not less real for being made of field rather than of smaller solid things. What changes is only the answer to the question, and it turns out the answer is stranger than the question deserved. We asked what holds up the weight of the world, and we expected to find something heavy at the bottom, and there is nothing heavy at the bottom. There is a force so strong it cannot let go, an energy that cannot get out, and the two of them together make everything you have ever held. Rutherford's undergraduate sat in the dark, counting flashes on a screen, and found the nucleus. 100 and some years later, we can compute the proton's mass on a machine that fills a room, and we still cannot say where its spin lives, and we're digging a tunnel on Long Island to ask. The strangest thing beneath every proton is not any single fact. It is that the substance of the world, all of it, is not substance at all. It is a knot in a field that will not come undone, and you are holding it.